Hi everybody, welcome to another video in Calculus 3. We go to section 15.6, tangent planes and linear approximation. So this is the analogy of what we have in Calculus 1, tangent line and linear approximation. Right. So before we go to that point, notice here we only find the equation of a tangent plane. So a plane, because the tangent plane is to a surface, and the surface can be represented two different ways. It can be a function of two variables x and y. If we move everything on one side, we have the equation in the implicit form. It is the level surface where z equal to a constant. For example, not z equal to a constant, where f equal to a constant. I'll give an example. Actually, we do something very simple, like x squared plus y cubed, for example. That is the function explicitly given. Z is a function of x and y. Now if we move everything on one side, we have x cubed, x squared plus y cubed minus z equal to 0. And in this case, we have the function of three variables, but we make that equal to a constant. So that is the level surface. So we make that equal to a constant. So the function of three variables, yes, but that equal to a constant. So that make it a level surface. And we will make it equal to a function of three variables. Yeah. Make that function of three variables equal to that equal to 0. So we have a level surface because that equal to a constant. Right. So we approach, so we represent a surface two different ways, and there will be two different ways to find equation of a tangent plane. And the idea of the tangent plane is just like Calculus 1, where we have a curve and we have a tangent line. When it is close to the point of tangency, the curve is close to the line, and so we can use the line to approximate the values of a curve. And that is the linear approximation. Same thing here, except we have two-dimensional or three-dimensional. We have a surface and we have a tangent plane instead of a curve and a tangent line. So we just add a dimension to it. All right, how do we do this? Right, first, tangent plane for a level surface. So first we find the equation of tangent plane for the level surface, that everything equal to 0 for an equation. Alright, actually we did this in the previous section. Let f be differentiable at the point and the gradient is not equal to a 0 vector. So this is a 0 vector, not a 0 number, because the gradient is the vector partial derivatives. And the plane tangent to the level surface is given by this, because as I mentioned earlier, for the previous section, when we have a level curve, when we calculate the gradient, it could be that point or that way. The gradient is orthogonal to the tangent vector to the level surface. So the gradient, this is the gradient, it is orthogonal to the tangent vector, and the tangent vector is given by x minus a, y minus b, and z minus c, simply because we have a point x, y, and z, and the point here we know is a, b, c. So subtracting the 2 points, we have the vector dot with the gradient must be equal to 0 because they are orthogonal. So either we write in this form, or we can say the partial derivative times x minus a with respect to x times x minus a with respect to y times y minus b with respect to z, z minus c. So this is the equation of a tangent plane to the level surface. Right, so simple enough. Right, here the example, find equation of the plane tangent to the ellipsoid here at the point. So we do is just find the partial derivatives f with respect to x. Here, derivative of x squared is 2x, and then divide by 9. It's a constant, so stay there. Derivative with respect to y is 2y over 25, and derivative of f with respect to z is 2z. We evaluate at this point. So at the point x equal to 4, x equal to 0, y equal to 4, and z equal to 3/5. We have f x of 0, 4, and 3/5. I'm going to put 0 in for x. That equal to 0. Then I put 4 in for y. So we have 8 over 25. And then we put 3/5 in for z. Give us 6 over 5. So as simple as that. So we find that, and then we just have the equation of potential plane. Just write down. If we take the derivative with respect to x at the point then we will multiply by x minus x values of the point, plus if we take the derivative with respect to y, and we had xy minus the y values of the point, and then we have z times z minus the z values of the point 3/5, and that equal to 0. Or we can write in the dot product form, but I write like this. So we have 0 times x minus 0 plus 8 over 25 y minus 4 plus 6 over 5 over z minus 3/5. Right. So yeah, so that is the equation of a plane. If we want to, we can multiply it out. I will multiply it out. So it gives us 8 over 25 times y. 8 over times 4, so my minus 32 over 25 plus 6 over 5 z and minus 18 . At 18 over 25 equal to 0. If we want to, we can multiply everything by 25 and we get rid of all the fraction. Rid of all the denominators. So multiply everything by 25, we have ay. And multiply by 25, that gives us 32 and minus 18, so that's minus 50. but multiply by 25. 5 and 5 cancel out, we have 30z. And then 32 and 18, that's 50 over 25, so that minus 50. Right? Yeah. Yeah, just like that, find partial derivative. And then with respect to x, multiply by x minus the point. With respect to y, multiply by y minus the point, and z, same thing. And then the point should be given. Then we just simplify. Right. Next, find equation of the plane tangent to the surface. This. So I write the function. Move everything on one side, and we'll make that. It's a big function, f of x, y, z. Let's move everything to the left-hand side. Yeah, and this function should be equal to 0. Or equal to 1. It doesn't matter. We can use that as long as it is equal to a constant, because the level set, that should be equal to a constant. Right. Let's write differently because we might not have enough space here. So derivative with respect to x. Derivative with respect to x, this function, only one x there, y and sine z is constant. Derivative of x with respect to x is 1. So we have 1 times y sine z. Derivative with respect to y, there's only one y here. Derivative of y is 1. X and sine z is constant, so we have x times 1 times sine z. And derivative with respect to z, sine z, derivative of sine z is cosine z. So we have that. Now we evaluate at this point. Derivative with respect to x as the point 1, 2, and pi over 6. This function, we're going to put 1 in for x. There's no x there. There's 2 in for y. And z is pi over 6. Sine pi over 6 is 1/2. 1/2 times 2 is 1. Partial derivative with respect to y at 1, 2, and pi over 6. This is derivative with respect to y. X is equal to 1. And z is pi over 6. Sine pi over 6 is 1/2. And we have 1/2. And then partial derivative with respect to z at the point. We still have x is 1, y is 2, and cosine of pi over 6. Cosine pi over 6 is square root 3 over 2. So we have 2 square root of 3 over 2. And so that's just square root of 3. Right, so we have that. And then the equation of tangent plane to the level surface. If we take derivative with respect to x at the point, then we will have x minus this values. If we have derivative with respect to y, then we have y minus the y values of the point. And if we have derivative with respect to z, we have z minus the z values of the point equal to 0. And I will just put in the number. 1 is the partial derivative with respect to x times x minus 1. With respect to y, 1/2 y minus 2, and then square root of 3 z minus 5 or 6. Right. And then we'll just simplify this if we want to, or we're just going to leave it like this if we want to. Because we have the equation of a tangent plane. Actually, I'm just going to leave it like this. Right. So that is the equation of a tangent plane to a level surface. We use this equation. Next, we'll find the equation of a tangent plane to a function z equal to f of xy. So what is the difference here? Actually, just think about it this way. One, we have z equal to f of xy, right? Now, if we move everything on one side, we have f equal to f of xy minus z. And then we will write partial derivative of x at the point, let's say ABC, times x minus a plus with respect to y, ABC, y minus b, and z, ABC, z minus c equal to 0. So we have that equation. Notice now, if this is the function, this is going to be equal to what? Just f of x. Right? Because the function only x, y there. So we just have partial derivative with respect to x at the point AB times x minus a. And this is f sub y, derivative with respect to y from that. AB, y minus b. And what's this? Derivative of this with respect to z will be minus 1. Then we have z minus c. And we'll solve for z. Let's say f of x, ab, x minus a, f sub y, ab, y minus b, minus z, plus c. I just moved the z on the other side. So z equal to f of x, ab, so derivative with respect to x, x minus a, derivative with respect to y, y minus b, and move z to the other side, and then plus c. C actually is the values of z at the point. So c actually equal to the function at a and b. So we have this equation, which is what we have here. So this actually is c, and move to the other side we have z minus c. That's what we have here. So there's certainly the relation between the two forms of equation of tangent plane. But either we move everything on one side and make it equal to 0, and the left hand side equal to f, and then we do that for the level surface. or we're just going to use this equation. Either way works. Right, I'm going to do both for this problem. Right, this problem. Find the equation of tangent plane to the paraboloid that. So this is a little f, the explicit function. So we take derivative with respect to x. Negative 6x. And then we take partial derivative with respect to y. Negative ay. Next, at the point 2, 1, and 16, meaning x is equal to 2, y equal to 1, and z equal to 16. So, at 2, 1, there's no z here, but just say it doesn't matter. Partial derivative with respect to x. We don't really need the z in the function because the function only have x and y, so we just have x and y. Negative 6 when x equal to 2, so we have negative 12. Derivative with respect to y. Negative ay plus negative 8. Right, and then I will write the equation. Equation z equal to f of ab plus derivative with respect to x. X minus a, derivative with respect to y. Y minus b. Right. Let's put on the point we have. What do we have? From here, a is equal to 2, b is equal to 1. What is 16? Well, 16 is the values of the function when we put 2 and 1 in it. So we can check z equal to, I'm going to put 2 in for x and 1 in for y. 32. Right, let me just write this first. Fz is equal to the function 2 and 1. So I put 2 in for x and 1 in for y. So 32 minus 12 minus 4. 32 minus 12 is 20 minus 4, so that's 16. So indeed, 16 is the values of the function at 2 and 1. So x, y, put those in, give us z. So we have 16 is this one. Derivative with respect to x, negative 12. With respect to y, negative 8. And the a is 2 and b is 1. Right. Put everything in the equation. So we have z equal to 16 minus 12, x minus 2 minus 8, y minus 1. Right. I'm going to leave it like that. Right. So that's good. Now let's assume that we don't want to use that formula. We prefer to use the equation of tangent plane for the level surface. So what we do is we move everything on one side. From this one, we will let move the z to the other side, or move this to the other side, either way. Actually, let's say, let's be more precise and say the function f, capital F, is a function of 3 variables x, y, and z. I'm going to move everything to the left hand side. It will be z minus 32 plus 3x squared plus 4y squared equal to 0. So we'll make that equal to z. And then take partial derivative with respect to x, with respect to y, with respect to z. With respect to x, 6x. With respect to y, ay. With respect to z, 1. Now we will evaluate at the point 2, 1, and 16. Derivative with respect to x. Put 2 into base 12. Derivative with respect to y. Put 1 in for y is 8. And derivative with respect to z is 1. And then finally we will have 12. That derivative with respect to x times x minus the point plus derivative with respect to y times y minus the point, and then plus derivative with respect to z. So I'm using this equation of a tangent plane to the level surface, and then z minus 16. Right? I just multiply this out. That's z minus 16, and I move everything to the other side. So if we do that, we will have z equal to 16 moved to the other side. Negative 16 moved to the other side becomes positive. This move to the other side becomes negative. This move to the other side becomes negative. So to see those two equations are identical. So that's the way it should be. So whether we find the equation of a level surface or just do a function, it doesn't matter. We might prefer just move everything on one side, make that equal to 0, and then just do the dot product equal to 0. So either way works. Right. Next, find equation of tangent plane to the surface. This one given in the function because z is a function of x and y. Right. So we have z is the function of x and y. Now we take the derivative with respect to x, with respect to y, and then put in the point, just like that, right? So derivative f with respect to x. Notice that we have x here on the x square and x here on the exponent. So x show up in two different places. So that means we have to use the product rule. So the product rule, derivative of the first one is 2x times the second function plus the first function times derivative of the second. I'm going to use the chain rule for that. Derivative of e something is e to the something, and derivative of that with respect to x. So we use the product rule here. U prime v plus u v prime. We have x minus y on the parentheses. So we have 2x e to the x minus y, and then x squared e to the x minus y. Derivative of xy with respect to x is just 1. Right. Right, so I'll just have that. Now derivative with respect to y. Now y only show up in this place, one place, so we don't need to use the product rule here. X squared is just a constant, so we just have constant there. then the chain rule is still e to something and derivative of the exponent with respect to y. So we have x squared e to x minus y. Derivative of this with respect to y is -1. So we have negative x squared e to x minus y. So those are the partial derivative. We will evaluate at 2 and 2. Derivative with respect to x at 2 and 2. I'm going to put 2 in for x and 2 in for x. I mean 2 in for y. E to 0 power is 1. E to 0 power is 1. And that is 4. And 4 gives us 8. Derivative with respect to y is at 2 and 2. We put 2 in for x. And 2 in for y. E to 0 power is 1. And here we have -4. So, and then the formula equation of tangent plane to a surface is equal to f of a plus b plus derivative with respect to x at ab, x minus a, derivative with respect to y at ab, y minus b. Alright. The difference on this one and the previous one is we only given x and y, we don't know the z values. The previous problem, we know the z values. So here we have to calculate. So I'm going to write here at 2 and 2, f of 2 and 2. I'm going to put 2 here. And e to 0 power is 1, so that is 4. So let's see what we have. 4 here for the values of the function. 8 for partial derivative with respect to x. And -4 for partial derivative with respect to y. And a is 2 and b is 2. So the equation is z equal to 4 plus 8 x minus 2 minus 4 y minus 2. Right, so just like that. Right, so straightforward. The two formulas, one for the level surface and one for just a function. Right, now the application to that. With earlier, I did mention that the reason we need the equation of a tangent plane is just like the equation of a tangent line. We use the line to estimate the curve. Now we use the plane to estimate the surface. Had to be close though. If we want to estimate the values of the function way out here, when it's too far away, the approximation is not good. So the approximation have to be extremely close to the point of tangency. And if you look at the left hand side here, that is exactly the equation of the tangent plane. Right. So let's estimate something like this. Hopefully we don't need a calculator for this problem. Right, let's see. So usually when we have this, we're going to let that number be x and that number be y, or vice versa. Doesn't matter. So that's the first thing I will do is let x equal to 1.2 and y equal to negative 0.1 or 0.1 either way. But when we let that equal to those values, then we say this becomes the function of x and y, right? So put x in for 1 instead of 1.2 and negative 0.1 in equal to y, so we put that. So what we have here is the function. Next, we need to approximate something that is close. So what we do is we're going to choose the values that is close to those values, and the approximation is easy to calculate. So 1.2, why don't we choose 1, and negative 0.1, why don't we choose 0? Those values are close and it's easy to calculate. So this is what we're going to choose, something close to x and something close to y. We choose those values and then we just have that. Let me just write the formula and then we determine what we need to find. I'm not going to write z, just write L. It's the linear approximation. Even though it said it's linear, but there's no, this is not a line, this is the plane, right? It's not a line. Function of two variables, so that is a surface. But we mean linear does not come from a line, but linear meaning there's no power here. There's no power of x or y. So L linear approximation equal to the values at a and b plus partial derivative x minus a partial derivative with respect to y minus b. Right. We'll go back to this formula later. Right. Now let's just find what is the values of the function. This is the function, right? So the function is x e to the y, and at the point a equal to 1, b equal to 0, or we say at the point 1 for x, 0 for y, f of 1 and 0, 1 times e to 0 power at the point 1 and 2 is equal to 1. So we know that this is equal to 1. Next, partial derivative with respect to x. Partial derivative with respect to x, derivative with respect to x is 1, e to the y is constant, so just have 1 times e to the y, or just e to the y. Now evaluate at 0 and 1, derivative with respect to x at 1 and 0, 1 and 0, sorry. 1 and 0. I'm just going to put 0 in for y because there's no x. So that is 1. Derivative with respect to y. Derivative of e to the y is still e to the y, where x is a constant. Then we evaluate at 1 and 0. Derivative with respect to y at 1 and 0. 1 for x, e to 0 for y, and that also 1. Solve number 1. Right, and then we do have x equal to 1.2 and y equal to negative 0.1. Just substitute everything in here. So the linear approximation equal to 1 plus 1. X is 1.2 minus a 1 plus 1 for the derivative. Y is negative 0.1 minus b 0. So we have 1 and 1.2 minus 1 is 0.2 and 1, and that's minus 0.1. So we have 1.1. Right. So let's just use a calculator to approximate. If we have the calculator, you see, we have 1.1 and the calculator have 1.085. So it's like close enough. The closer the point is to A and B, the better approximation is. But this one is close enough. Right. Let's try it for this one. So when we have two numbers, let one of them be x, the other one is y. So x be 2.1 and y 1.05. Because of that we have the function x and y. Square root of x cubed y squared. Right. And now we choose something that is close to it. I'm going to choose 2 and 1. That is close to it. And not only the close, so close is only one criteria. The other criteria is that if we put 2 and 1 in here, number is doable by hand. I mean, because if not, we use a calculator. But if we put 2 in for x and put 1 in for y, we have square root of a plus 1, square of 9 is 3. So certainly we can do this by hand. So the choose a and b for one is close to the point, and the second point is easy to evaluate this by hand. So that is also a criteria, something that is easy to evaluate. Right. I'm going to write out the linear approximation and then calculate what do we need. Right. So linear approximation, a function at a and b, partial derivative at a and b, x minus a, partial derivative with respect to y, y minus b. Right. Now let's find all of those function and derivative. We have the function x cubed y squared. Now evaluate when x equal to 2 and when y equal to 1. 2 cubed 1 square, that is 3. Now we take derivative with respect to x. Alright. And let's rewrite the function as x cubed plus y squared to the 1/2 and use the power rule. So the power rule with the chain rule here. So derivative of something to the 1/2 is 1/2 that to negative 1/2, and then derivative of inside with respect to x. So we have 1/2 x cubed plus y squared to negative 1/2, and derivative with respect to x here is 3x squared. Right. And then add 2 and 1. We have 1/2. Sorry, I should have more space for this one. X is 2, y is 1, and then 3, x is 2. Right, I just use the calculator here. I just use 0.5 if I want to. Right. 2 cubed and 1, so that is 9, pretty much, to the negative 1/2. And then 3 times 2 squared, that is 12. That's 2. And then we'll take the derivative with respect to y. Also, the chain rule, 1/2. This to negative 1/2. And derivative with respect to y. X cubed minus y squared. X cubed plus y squared. Right. So we have 1/2. X cubed plus 1, that's still the same thing. And derivative of y squared with respect to y is 2y. Right, then we put in 2 and 1, 2 in for x, 1 in for y. So we have 1/2. 2 cubed, 1 square, negative 1/2, times 2 times y is 1. So pretty much we have this, except instead of 12 it's going to be 2. Right? So this is 1/3. Right, so if I own the values, 1/3 is derivative with respect to y, 2 derivative with respect to x, and 3. So 3 is for the function derivative with respect to x, 2 derivative with respect to y, 1/3. X is 2.1, y is 1.05, a is 2, and b is 1. So L equal to 3 plus 2, x 2.1 minus 2, plus b, plus 1/3, y minus b, so I have 3, that's 0.1 times 2, 0.2, 1/3, 0.05. 3 plus 0.2 plus 1/3 times 0.05. We can change this to a fraction if we want to, but in spirit of approximation, we just say this is 3.21667. Right, so that is our approximation. What is the exact values if we have square root of 2.1 cubed plus 1.05 square? To see, I have 3.21667, the exact values 3.219 something. So yeah, at least it is correct up to, I should say, 3 figures, 2 decimal places. So it's not bad. So that is when we use the approximation, linear approximation. Also, we have to have this right below the equation of tangent plane, because we use the plane to estimate the surface, just like when we use the line to estimate the curve. Next we go to differentials, meaning the difference. So Let f be a differentiable function at the point the change in z. So we're looking for the change in z, where a go from a plus delta x and b go to b plus delta y. Is denoted by delta z, and will be just this. So compared to the equation we have earlier, let me just start quickly and look at this equation here. Now if I move the f of ab to the other side, I have z minus f of ab this between the z and another value of z, so this is delta z, the new values, the old values equal to that, and that is exactly what we have for differentials. Oh, I mean the change in z given by that. So the differential dz is equal to that. Right, so simple enough, right? Now, use differential to approximate the change in z, where we have the changes from 1.3 to 1.1, 1 and 3 to 1.1 and 2.9. Right, so we have the change in z approximately equal to the derivative with respect to x at ab times the change in x plus derivative with respect to y at AB times the change in y. Now, we go from 1.3 to 1 and 3 to 1.1 to 2.9. So we go from 1 and 3 to 1.1 to 2.9. So initial values is going to be a and b. So a is 1 and b is 3. Those are initial values. And then the changes, delta dx or delta x, final minus initial, and dy or delta y, final minus initial. So you have dx and dy. Now we just need to find partial derivative with respect to x, with respect to y, and we have it. The function is this, z equal to x squared plus y squared, derivative with respect to x, 2x, derivative with respect to y, 2y. And then at the point 1 and 3, derivative with respect to x is 1 and 3. 1 in for x, we have 2. Derivative with respect to y, 1 and 3. Put 3 in for y, 6. So simple enough. And I'm going to put 2 and 6 here. And of course we have the dx and dy, 0.1, 0.1. So delta z approximately equal to 2 times 0.1 plus 6 times negative 0.1. So we have 0.2 minus 0.6 is 0.4, negative 0.4. Right, so let's see how good the approximation is. So originally we have 1 and 3, so 1 square plus 3 square. Originally, that's what we have. Now the 1 becomes 1.1 and 3 becomes 2.9, and we will take the final minus initial. So we have negative 0.38. So that is the actual difference, negative 0.38. The approximate of the change is negative 0.4. So should be close enough, right? So just use that form. Now let's look at an application problem. I suppose we have the cylindrical can. 30 centimeter for the radius, and the height is 55. So we have the cylinder with the radius is equal to 30 centimeter. The height 55 centimeter. The volume, what is the question? The percent errors in measurement do not exceed 0.2. So this is the percent error, not the absolute error, meaning that the percent, the worst case scenario is it's going to increase or decrease by 0.2. Right. So, by the way, yeah, let's just read the problem. Approach the worst possible error in the volume. Assume that the size and the end of the can is with negligible thickness. So the volume of a cylinder is pi r square h. So that is the function. Right. So what is the errors? The errors meaning is 0.2. So what does that mean? This is the percentage error, 0.2. Does that mean it's not 20%? Obviously, 0.2%. So we will say the change in the radius have to be less than or equal to 0.2% of the actual radius. That's what it means. The percent error do not exceed 0.2. Let's rewrite this. Is 0.002 r. I might put the absolute values here because the error could be 0.2% more or 0.2% less. Let's put the absolute values there to be precise. The percentage error for the height is 0.5, but do not exceed 0.5% of the height. And now they said, what will be the worst error in the volume? So what do we do here? So instead of writing in that form, now I use z, I use v instead of z, and r and h instead of x and y. So instead of writing delta z this is approximately equal to now we use different variable. Delta v equal to we're still using v here as the function with respect to x at a and b. Delta x, or dx. Instead of x, we use r, and instead of h, y, we use h. Now, let's find the partial derivative. derivative with respect to r is only r here. Pi and h are constant, so we have 2 pi r and h. And derivative with respect to h, only variables h there, pi r squared is constant. Derivative of h is 1, so pi r squared and h. Now, since we want the worst possible error, we have to choose the maximum of those errors, and we substitute in here, right? So what we do is we're going to put that in for v, derivative of v with respect to r. So we have that one, 2 pi r and h. The worst possible error is plus or minus. That's I'm going to use the error here. For r is 0.02, 0.002 r. Derivative with respect to h is pi r squared h, and dh, the worst possible case, is 0.005 h. Sorry, there's no h here, right? Right. We do know r and h equal to that, but we're not substituting yet. Let's see what happens. Let's scramble here. And that gives us 2 times 0.02 is 0.04, 0.004, right? And then we have pi r times r squared h. And then here we have 0.005 pi r squared h. What we see here is pi r squared h is v. So we have 0.004 v plus 0.005 v is 0.009 v. Now, the reason that we choose those values and put in here because we want the worst possible error. It could be positive, it could be negative. If we want to, we put negative, still the same thing. But I would choose positive for easier calculation. We have to choose both of them positive. Let's say instead of making the can with exact size, we make it a little bit bigger on the radius and bigger on the height. What would be the volume? What would be the worst possible case for the volume? So we have 0.2% for the radius and 0.5% for the height. The total end up will be 0.9% in the volume. So if we limit the error in the radius by 0.2% and the error in the height by 0.5%, the total add up to 0.9% in the volume. So the error in the volume will not be more than 0.9%. Right. Once again, we choose the highest values because we want the worst possible error. So that's why we choose the highest values, put in there, and that's what we have. So the question is, approximate the worst possible error in the volume, and we said the worst possible error will be 9.9% of the volume. And if we want to, we can find the volume, put 30 and 55 in here. We can actually find the worst possible error, not the percentage error. So the percent error, and this is the worst percent error for volume is 0.9%. And if we want the worst error, it is 0.9% of V, or 0.009, and V is pi RH, pi R square H, and R is 30 and H is 55, so we actually can calculate. Yeah. And the unit will be cc because centimeter cube. Yeah, we'll just calculate that. So we have that. About 1000 cc. Whereas the volume is pi R square and H. So the volume is about that much. And then the error is this much. So the worst possible case is about 1400 centimeter cube, and the volume is this much. All right. So with that, we cover section 15.6, equation for tangent plane, in two different forms. It could be equation of tangent plane to the level surface, or equation of the tangent plane to a function. And the equation of tangent plane to the function, we use that for linear approximation. And then of course, from that we can derive the formula for the differential dz. Alright, so I'm going to stop the section here. As always, thank you for watching.